earthquake, well, volcanic earthquakes. So volcanic earthquakes can also generate tsunamis. So here's our, we call it the mechanism CLVD. So usually CLVD earthquake are associated with volcanic activities. And here's a plot for the CLVD events. The CLVD, vertical CLVD beach ball look something like this. And well, this kind of event is not really easy to explain, but some researcher came up with some possible physical mechanism like fluid flow and volumetric changes or ring fault mechanism. So here's some, the interesting thing about CLVD event, it may happen at the same location with almost same magnitude and during a certain period of time. So this is the CLVD events in the Smith's caldera in Izubonin Island. So again, this is south of Japan. They call this Torishima tsunami, even though I mean this is not the location is not Torishima. The tsunami was recorded at Torishima Island, but this caldera is called Smith's caldera. And yeah, we have an event in June 1984 with magnitude of 5.9, and then another event in 1996. So that's about 12 years after the first event. The magnitude was 5.6. And then 10 years after that, in 2006, magnitude 5.9 occurred. And then 9 years after that, in 2015, another 5.9 CLVD event occurred. So this really happened several times with almost same magnitude at almost same location. And here's our tsunami waveform from those three events. So the red lines are from the 1984 event, gray is from 1996, and the black is from 2006. The green lines are from the 2015 event. So you can see the similarity between these waveforms are very, very similar. And then there's also another location. So this is not in Japan. So this is in New Zealand. So in 2004, we have a CLVD event. 2009, we have a CLVD event with magnitude of 5.8 in Curtis Island. So it's located here. This is near the Curtis volcano. And then the centroid location for the 2017, just north of the one for the 2009. The 2017 earthquake has also magnitude 5.8, just same magnitude and same fault mechanism. And here, so here, this earthquake located near these two islands called Gusman Island and Curtis Island. So this is Curtis Island. And these islands were uplifted multiple times, according to this report by Doyle and Singleton. So they have ships running around the Kermadec Ridge through these islands, and notice this island were uplifted for a total of 18 meters during the period from 1887 to 1979. So here's some volcanoes around, along the Kermadec Ridge. So the Curtis Island is located here, south of the Macaulay caldera, better known caldera here. And then we have Raoul Island. This is the northernmost island of New Zealand. Well, it's really called island. The other one, the other northern of Raoul, probably just very small rocks. Um, yeah, this is the Curtis Island is south of Raoul Island, but about 1,000 kilometers north of the North Island of New Zealand. For this event, we have record of tsunami. So here we have two stations in Rhode Island, and then we have 1, 2, 3, 4 station recorded the event on the main island, the North Island of New Zealand. So here the blue is Lotin Point, Tauranga, North Cape, and this one is from the 2009. So in 2009, we don't have the Raoul Island station. So yeah, it's a shame. So well, in also we don't also have the tide gauge in Great Barrier Island and Auckland in 2009. We don't have the record, but we do have records for those events in these 4 stations: Lotin, Tauranga, North Cape, and Gisborne. So if you look at the Lotin Island, Lotin Point, sorry, the wave are almost, the two waves are almost identical. Also at Tauranga. Yeah, but the maximum amplitude was recorded about, the maximum amplitude was about 50 centimeter here, recorded in Raoul Island, gauge station, Raoul Fishing Rock. Now here's some mechanism that we propose. So probably because we have the CLVD source mechanism. So the thing is, so it's a bit difficult to explain this event because the CLVD was recorded at depth of, what is it, 13 kilometer, right? So if we use 13 kilometer and then make a source model from the fault mechanism and run the tsunami, the simulated tsunami from that model is very, very small. So not as high as the observation. So we couldn't explain the tsunami wave using that 13 kilometer depth even. So what we try to do is find a model that can explain seismic wave and tsunami wave. So probably the CLVD event at depth of 13 kilometers is located in this deep magma chamber, and then it's give some kind of pressure to the shallower magma chamber. And here, maybe a tensile crack was triggered because of this pressure from the source number 1. So this tensile crack become source number 2. So this tensile crack generated the uplift that can that explain the tsunami data. But we, well, for crack model, so the crack model in surface almost cannot generate seismic wave, so that the seismic wave can be explained by the deeper part. So that's our explanation. So this is the sea surface displacement model. The uplift was almost 4 meters here. This is the Curtis Island and this is Gusman Island. And here's just a cross section of the model. So the model from, yeah, we have this, for this event, we had to do a 2-step inversion approach. So first we just estimate the sea surface displacement and then find out how much the shallow tensile fault would look like. So this is the model from the tensile fault and the cell CLVD. Another mechanism proposed by other researchers, including um, ring fault mechanism. So they think we may have shallow magma chamber, and surrounding that magma chamber, we have outward dipping or inward dipping ring faults. So this is a schematic diagram for inward and outward dipping ring fault located above a shallow magma chamber. So the ring faults are basically cone shaped in 3 dimensions. So you just need to imagine this. It's a 3-dimensional ring. And here's some comparison between inward dipping. If we have inward dipping normal ring fault, we have this area go down, and for inward dipping reverse faulting, reverse ring fault, so we have outward movement here. For outward dipping normal ring fault, we have upward movement here. For outward dipping reverse ring fault, we have downward movement here. So this is kind of different kind of combination of inward and normal or reverse ring faults. Okay, those are slides for CLVD earthquakes. Any questions so far?
Thank you, Dr. Gusman. There is a question from Aldo in the chat box. He asked about the second wave of the tsunami wave is always worse, or it is not necessary. What do you think?
Hold on. I cannot see the
in the chat box.
Yeah, hold on. Cannot really see the chat. Okay, here we are. The second wave of the set of the tsunami wave, it's always the worst, or it's not necessary. No, it's not necessarily the worst, but like the Tohoku tsunami, the first was the largest, but it doesn't stop there. It's keep moving. But well, we can see the first one. Well, it's just keep coming and coming. So the first was considered the largest, but the second and third make it worse. Not really larger, I would say, in some places. But in other places, it was larger. And for the Palu event, the first was very small. So very small, people can survive the first wave. It was like a flooding, so slow, not so big. Well, it knocked down wooden houses, but people can still escape. Fortunately, they have these leading small waves, so most people, I mean, immediately knew something is coming, so they evacuated. The second was larger than the first one for the Palu event, so it really depend on the event. But the point is, the first wave is not always the largest one. So just if a place hit by a first tsunami wave, you still need to be careful. Yeah, that's the message.
Sorry, and how about the tsunami caused by the Anak Krakatau eruption on 2018? About the first and the second wave. Is there any comment about that?
Yeah, the videos were not really showing all the sequence. Not like in Japan, we have so many videos from CCTV, and then people are capturing. But the videos from Anak Krakatau was brief, mostly are brief, and they are only showing the first wave. But looks like the first wave was big, and it's just many people were killed by the first wave. Yeah, well, I don't really know. Fortunately, sorry about that. But the characteristic of some characteristic are the same, like wavelength. We consider the wavelength of tsunami from Anak Krakatau and Palu are short, so they destroyed the area. I mean, on the, just like 100 meters from the beach, or like 50 meters from the beach, completely destroyed. But like 100 or 200 meter from the beach, the wave are so small. I mean, they decay very quickly, so the destruction are really within this 50 meters from the beach.
Okay, thank you. Is there any question from the participant? Please raise your hand or put your question in the chat box.
Okay. Maybe should go to.
Okay, please open your mic. Di posisi Sobat.
Mr. Aditya, I want to ask about the factor in tsunami, the factor that could make a tsunami. Which one is more important, the magnitude or the epicenter of the earthquake or the volcano or the volcano eruption? Which one is more important? Because if I see from the MKG report, sometimes it report that there is an earthquake with 5.6 magnitude, but there is no tsunami potential.
Yeah, well, I think that's the difficulty right now. So the current tsunami early warning system depend on they can also only work for earthquake events, not really for volcanic events. So the volcanic tsunami mechanism is quite different than tsunami-genic earthquakes. Yeah, right now we cannot really tell from the magnitude. So the magnitude, as I mentioned here in the CRPD event, if we use the magnitude, the predicted tsunami is very, very small. I mean, much smaller than the actual observation. So we will have underestimation if we rely on magnitude. That's basically. If that is because we are using if we use the standard earthquake fault model, we will have a bad underestimation. But here's in this study I provide crack model that may generate large tsunami. So probably if we want to accurately predict tsunami from, I mean, volcanic earthquake, we should use the crack model instead of typical double couple model.
Okay, thank you, Mr. Aditya.
Okay, thank you.
Yeah, for Anak Krakatau, even Anak Krakatau, the seismic wave was generated by the landslide. I think somebody's trying to find the landslide potential from the seismic wave. Yeah, still need to learn about those things. Sorry, I hope I can answer your question. Was it answer your question or not?
Maybe partial. Not. I don't. I still don't understand which one is the biggest factor, the magnitude or the location.
Well, I think the question should be what mechanism is it, not really the magnitude or location. So, yeah, what mechanism involved in that earthquake?
Okay, thank you. Thank you, Dipo Yusafat. Is there any question from you? Clear?
Clear, Mr.
Okay, thank you. Okay, I will to invite the other participant. If you have a question or comment, please raise your hand. Perhaps from Pak David, you have any question, Pak David?
Not yet, Pak Zul.
Okay. Okay, we will continue.
So can you see the screen now?
Yes.
So next, it's
But
about
sorry, but not full of presentation view.
really. Desktop one. What are you seeing right now?
In my screen, still loading.
Can you see my full screen?
Not yet. Still the PowerPoint window. There are two PowerPoint window. It's just you share the desktop. I think you can change to share the presentation view of PowerPoint. Nah, yes. Okay, it's gone again.
How about now?
Yeah. Okay.
Is it full screen?
Not yet. It's still present side, not present. Yeah, it's clear, full.
Okay.
Excuse me, I can see you. It's full screen now.
Can you see now?
Yes.
All right.
Okay.
Okay.
So next is another mechanism that I want to talk is what is it? The pyroclastic flow and the flank collapse. So those, I mean, we have example from Krakatau and Anak Krakatau events. So here is just on the left-hand side, just from newspaper back in 1982. So we have a few of Krakatau here, the Krakatau volcano, and then here is the view for Anyar, and here this is also Anyar, and we have the Anyar first point here, the lighthouse. So still have a lighthouse right now, but that if somebody ever visited Anyar, you might notice there's a lighthouse there, but that lighthouse was built after the lighthouse shown here was destroyed by the tsunami. So this one was made of bricks, and the other was by it was not bricks lighthouse. So it's from, I don't know, iron or metal or something. So, but the foundation you could, I don't know if I haven't been in Indonesia for a while now, but when I was there, I could see the remnants of that lighthouse. So we can found brick foundation, and even we can find debris of bricks like several hundred meters from the coast. So it just, if you visited the lighthouse, you would find a river there, and you just follow the river upstream. You could find some debris of bricks, red bricks, from the lighthouse. And then if you dig hole there, you may find layers of corals. So those are evidence of tsunami. Unfortunately, I visited that area many times. I mean, several times, but at that time, I don't have. I mean, digital camera was not so cheap at that time, so I don't. I was trying to find photos of those deposit, the coral deposit, and the bricks, but I couldn't find it. I'm sorry, but yeah, maybe if I visit that place again, I will take a lot of pictures. Yeah, this is a very interesting place to visit. If you want to visit this lighthouse, just try to find some the like coral layer or bricks. You may find one. You may find some. Okay, and here's basically the evolution of the Krakatau Island. So this animation is just from Wikipedia. So started from 1880, we have 3 peaks here in Krakatau, and then it's called Perbuatan, Danan, and Rakata. And after the eruption, we have small, tiny temporary islands. And then in 1900, those islands were gone. And then we have Anak Krakatau emerged in 1927. And then, well, this animation is up until 2005, I think. So the height was 300 meter, and now it's gone. So this is the last one was, I think it was 600 meter. This was taken in July 2018 before the flank collapse. Okay, pyrocaustic flow, just basically high speed avalanche of hot ash and rock and fragment and gas. The pyroclastic flow move down the side of volcano, destroying everything in path, and then the speed can be up to this speed this is made by American. The speed is mile per hour, but it's like 100 to 700 kilometer per hour, and the temperature can be up to 700 centigrade. So here's just a photograph of pyroclastic flow entering the sea. Now here we have an interesting experiment done by Borgwin. So here's a laboratory experiment done by Borgwin 2020. They tried to model the dynamic of pyroclastic flows entering the sea. The experiment set up, they have horizontal channel, just rectangular cross section. I mean, the length is like 7 meter long and 0.8 meter high. And the width is, I think it's like 20 centimeter or something. So this here, 0, they define this as the shoreline. And on one side, they have channel, and then they have volume of reservoir. So it has a gate and then a mobile plate to release the volume, and then it's connected by a slope. And then hold on, yeah, then the angle here is, they try different angle, but most of the result is using 15 degree for the slope. And here this is the snapshot from from their high-speed camera. So this is a laboratory experiment of fluidized granular flow. So they have granular material and they fluid. I mean, they made it act like a fluid, and so then they release this granular materials on the slope and hit the tsunami. So basically, what they found, the dynamic of the process is basically they have a formation of initial just vertical jet like this over the water, and then after that they have a leading wave with this amplitude, and then they have some kind of turbulence here, and then some kind of mixing zone here underwater, and then the turbidity current is keep flowing down the slope. Yeah, well, the impact of the fluidized granular flow into the water basically have one initial vertical jet over water like that, and then two leading wave, and then after that they have like turbulence here. And here's some another study. In this study, they model the pyroclastic flow. So here in this model, they have two layers model. So they have different type of material. So they have dense type of material. So it's dense. So this eta here is the water surface, and this eta 1 is water surface, and then eta 2 here is the dense the thickness of the dense flow. So the rho is just density. So basically the dense material go under the water, so it push up the elevation like that. And the second material, they have light pyroclastic flow model. Well, again, this is just the thickness of the material, and then this is the water level. So in this model, they push to the side, and they also, because the water pushed to the side, they still have amplitude here. So they have tested with different density. So the density here is higher than the density of the light material. In their study, they use this bathymetry. So here's the bathymetry. They reconstructed the bathymetry from what's the publication? I didn't put it here. I forgot. But there's a bathymetry data before the bathymetry, but nautical chart for bathymetry before the 1883. So they used that nautical chart to get this map. So this is the Rakatau or the Krakatau Island. This is Sertung and Panjang. This is the Sulawesi Island. And then this one, this is bathymetry after the pyroclastic flow happened. So some parts are shallower. You can see, just look at this Sertung Island. We have different coastline here around the volcano, and basically this area become shallower because of the debris from the pyroclastic flow. And then C, this is just bathymetry after the caldera collapse. So the caldera collapse hypothesis was not favored in this study, I think, because it was they considered the caldera collapse took long time to complete, but the tsunami arrived much earlier than what they expected from the caldera collapse mechanism. So they think the tsunami from 1883 was mainly generated by pyroclastic flow. And here just the D is the bathymetric different water depth. So that is basically the pyroclastic flow material. Now this is how they do the numerical experiment. So they yeah, so here's initial condition for the pyroclastic flow. So we have circular pyroclastic flow model here. So this slice distance and flow height. So flow height is the y-axis here, and this x-axis here is the distance in this plane. So in here they use for in this graph is for the dense type flow model. Density is 1,100 kilometer per meter cube, and volume is 10 kilometer cube. The average speed is 107 meter cube per second. Yeah, they just push the. I'm really sorry about the voice. Yeah, background in the background. Yeah, so so at the beginning, so this is time 0.5 minute. So they push the material upward like that, and then after 2.5 minutes, we have this dash line going upward and then going up until the 10-minute line and then going back. And this one is this profile is the solid line is for the 15 minutes. So the process is first pyroclastic flow going up and then go down back and spread across horizontally. Now here's the elevation. What see surface elevation from model A. Model A is using dense pyroclastic flow. So you can see the material go under the water. And this one is the light pyroclastic flow. It's the water was pushed to the horizontally like that, but it still creates a tsunami. So the A is for the dense model, and then the B is for the light model. You can see the dense model generated much higher tsunami than the light model here. Yeah, it's quite interesting study by this Maino and Imamura. The paper was published in Journal of Geophysical Research. If you are interested in numerical modeling, go visit that. Uh, go read that paper. I have a copy of it. And then, yeah, that's for the pyroclastic flow. And any questions so far? No, if not, I'm going to continue.
I think not yet. The question from the participant, you can continue.
Okay, now this is about the Anak Krakatau event. So that is me with my friends here. The photo was taken in 2011, so it's probably somewhere here now. So this picture is for the Anak Krakatau after the 2018 eruption. So the old summit was here, and you can see from this photo the summit somewhere there. Now it's gone. It's amazing, isn't it? So I was there, and fortunately the Anak Krakatau did not erupt in 2011. So this is what happened after the eruption. The volcano has new crater here, and then completely different shape now. So amazing. So this is what happened. This is the sequence according to this Williams paper. So they use satellite imagery showing the evolving geomorphology of Anak Krakatau as a result of the 2018 eruption. Oh, well, it's until 2019, actually, January 2019. So a figure A, where's figure A? So this one, where's my A? Yeah, this one is before the eruption. And this one is also before the flank failure, but after the sequence started. C, where's the C? Sorry, this is A, B, C, D, E, F. Yeah, A, B, C. So this is after 8 hours after the tsunami. And then this one is the destruction of the summit. So even 8 hours after the tsunami, we can still see the summit. And then, well, this is just, this plot is just, hold on, A, B, C, D, E. Oh yeah, well, they regrowth. Apparently the volcano regrowth. So this is after the summit was destroyed, and this is after the regrowth. So here's the evolution of the island volcano. Yeah, so phase 1, they have strombolian eruption, and then phase 2, flank failure. So the tsunami was generated during this event. And then they have phase 3, the fan migration to the west. So you have kind of like underwater explosion here. And then this one, return migration of fan and strombolian eruption. And then they're rebuilding the cone. So, well, the tsunami event was happened in this phase 2. The tsunami generation event was happened here in the phase 2. Yeah, here's this map showed where the tsunami was recorded instrumentally by tide gauges. We have tide gauges in Bengkulu, Kota Agung, Panjang, Siwandan, Marina Jambu, and Binuagan. But we have very clear tsunami wave recorded at these 4 stations. Again, yeah, this is the Anak Krakatau before the eruption, and then this is the after the eruption. But as you can see in the previous presentation, well, this is probably this picture was taken in 2019. Well, yeah, this picture probably after 2019. So it's a bit tricky to model the landslide because we don't really know the volume of landslide that generated the tsunami. Should be, if this phase are true, the volume that the landslide volume that generated the tsunami is less than what the volume lost during the whole process. But anyway, so they have in this study, this is the actual tsunami record, and then they filter out the tide and the high frequency wave. They have this kind of wave. Yeah. So yeah, well, there was a interesting experience during the event. So I think it was discussed in Hagi web chat, WhatsApp group, and then people were debating which what is the cause of the tsunami recently happened in Sunda Strait. Some are, well, some are doubt that the tsunami was from the Anak Krakatau, but I was able to get the tsunami record from BIG, and then I can see wave, because we don't know. I mean, usually tsunami can be detected if we have, can be detected easily if we have record and an event time. But at that time, just one day after the tsunami, we don't really know the timing of the event, because the volcano has been erupting for some time, right? So we don't really know the tsunami source time. Yeah, that was the interesting ones. But I got the waveform here. I mean, I got the wave data here. So I just get the wave amplitude and then at each station, and I did back projection analysis, and then just trying to trace where's the source and what time is it. So using back projection, I could actually get a beam at the center of Sunda State, which is correlated with the location of Anak Krakatau, and I got the timing. So I just submit, I mean, just publish that in Facebook. Then soon enough, Compass Network contact me and want to have interview. Yeah, what that was interesting. Well, I wasn't there. I wasn't in Indonesia, so I wasn't really follow the news. But I got the data, and then track down the, I mean, pinpoint the location of the source, and then the timing with that back projection analysis. Well, yeah, now they know. Well, this is not, they're still assuming. So this is here in this, he said assume to be 22nd December at 13:55 UTC. So we don't really know actually when the tsunami was generated. They just assume the tsunami was here and do some modeling, and then they later confirm, well, this is probably when the tsunami happened. So that's how they basically do the analysis. Okay. Yeah. So here's a tsunami wave data, and then this team led by Muhari et al. They went to the field and collected tsunami flow depth and height, run-up height data. Here, the run-up is up to 15 meter here in Tanjung Lesung, and many of them are about 3 meters along this area. This is maybe along 50 kilometers along the beach. So yeah, post tsunami survey was done. I think it was 4 days. Yeah, it was 4 days after the event. They measured the flow depth basically, and they observed damage in Ujung Kulon, and they observed damage in Panaitan. This is Panaitan Island in Ujung Kulon here. We can see inundation distance of about 200 meters. And they also have this measurement here, about 3 meters here, and then you can see the tsunami height decay quite quickly. I think partly because the period of the wave is relatively short. So they have very high, almost 4 meters, and then less than 200 meters, the tsunami is gone here. And here some observation that they have also at the islands surrounding the Anak Krakatau. Here at Sertung Island Point A, you can see this limit of run-up, and this distance from the distance from this end to that end is like 200 meters. The height is about 40 meters here in this plot, but they said probably this is from a landslide. I mean, not because of the tsunami, but this is probably another landslide, and in return may also generate tsunami, probably locally. But this one, I think this one they think is from tsunami run up. Yeah, so probably, yeah, this one is probably from the tsunami. Hold on, where's my mouse? Yeah, this one C. This is probably from tsunami, and the height is like 15 meters. So they have 15 meters of local run up here. This is in Rakata Island. So Rakata is the remnant of the Krakatau Island. So here, this is the old Krakatau island. So it's not active anymore. So this one is the Anak Krakatau is located here. So C is here. So it makes sense. So the collapse is around here. The flank is located here. So the tsunami, the sliding is going to that direction, and we may have lots of tsunami in this area. And maybe this area, but they said B is probably not tsunami runoff. This probably landslide. So good, very excellent observation done by that group. And then here's also analysis, tsunami waveform analysis. So they calculated the average root mean square of the tsunami amplitude, and the blue shade just show you the duration of tsunami recorded at each station. So the duration here is only 7 hours. So for tsunami, 7 hours is short. So they think the short duration is due to the nature of short period wave of that tsunami. So usually the duration of subduction zone tsunamigenic earthquake can last for days, not hours, so for days. But here in this case, it's only a few hours. And here there's spectral analysis. Can see the tsunami has relatively short period, so only 10 minutes, 5 minutes here. This is just the dominant frequencies from the waveforms. Okay, I think I was almost finished. This is animation, very nice animation from Stephen Ward of flank collapse. You can see the cross section, very quick animation, but you can see clearly the flank collapse in this animation going down. This is only the soil, not the water. And then my last presentation is just this. Yeah, this is again the landslide, and this one is the animation. Okay, that's all I have right now.
Okay, thank you.
My presentation.
Thank you, Dr. Gusman, for your interesting presentation, interesting material that you deliver in this lecture. And I think before we go to the question and answer, I would like to invite all of the participants to turn on the video. We will take the photographs. Okay, 1, 2, 3, screen 1. And then 1, 2, 3, screen 2. Then the last one. 1, 2, screen 3. Okay, thank you. Then we'll move the question and comment. Dr. Gusman, we have 2 questions in the chat box. From the first one from Marco Delgado. I would like to invite Marco. You want to ask directly? If you want, but if you don't want, we'll read the question from the chat box. Marco asked about is the model type related to the VAI of the eruption, like a dense type model due to the higher VAI? Any comment about that, Dr. Gusman?
Yeah, so the model, yeah, I think it's based on the well, first of all, I'm not a volcanologist, so I don't really know the correlation between the volcanic intensity with the density of the pyroclastic flow. But yeah, what they use in their paper was they first find out what is the common density of the pyroclastic flow, and then use that in the model. So the input, it's not really the VI, but the input is just density of the pyroclastic flow. So they have different, they just tested different different density and the height, then the volume of the pyroclastic flow. So that's what they use. First, they've tried to find out the most likely density of the Krakatau event, and then how much volume ejected by the eruption. So that's how they determine the model.
Okay, thank you, Dr. Gusman, for your comment. Then the second question from Marco: how do you measure the height of the water flow when there is not a good reference to measure, like a building or trees, maybe like a low vegetation? Any comment?
Oh yeah, they use laser rangefinder. So usually they still need a reference, but they can go to the any point. I mean, at the, for example, coastline, and then they can direct the rangefinder to the end of the run up, for example. Then the rangefinder, the laser rangefinder, can find the height difference. So we go. I mean the height. Yeah, well, this one, I mean, the easiest way is to find the run up, the limit of inundation, right? And then we can measure the run up height. But if you, so what was the question? If there's no reference, yeah, I don't think they cannot measure anything if there's no reference, but should be something. So usually trees, so we can see like scars on trees, so that can be a sign of tsunami, or like broken branches of the tree. So if it's tall tree, you will find the lower branches broken, and that can be indication of at least how high the tsunami was. And if you look, I mean, you find the top branch still intact, then the probably tsunami didn't reach that high. So those are from trees. Well, trees can be tricky. Well, I personally never use trees. Well, not never. I mean, if there's no other option, I will use tree. But trees are tricky because you can. Some people just get like if there's something like plastic bag hanging on the trees, they will measure that. But I would probably think, oh, that probably from a splash or something. So I would prefer to measure the watermark on buildings. That was just like, for me, it's a gold standard. So if you like have a watermark from, you can see the limit of the watermark from the sediment. You can see clearly the line, and that I would prefer to take for measurement. Sand is also tricky. People would say, "Oh, sand, because sand, we have sand on top of roof," and then they would take that as a measurement. But I don't take those kind of measurement. But usually, if people in their survey report, they would say, what was the reference? They could say tree branches or sand on roof, something like that. So then other researchers might give a score to each measurement, like A, B, C, something like this.
Okay, thank you for your comments, Dr. Gusman. Then we have another question from Harun Tias. Is there any specific difference between a tsunami caused by a volcano and the tsunami caused by the earthquake?
Yes. So the period can be different. So like this one, well, yeah, we can see if we have waveform. So like this one, okay. Like the Anak Krakatau, the dominant period is like, well, it depends on the station, but it between 5 to 7 minutes. But for earthquakes, like subduction zone earthquakes, the like thrust faulting earthquakes, the period can be 20 to 50 minutes. So much longer period, and that longer periods mean longer wavelength, and then the longer wavelength means farther inland penetration, basically. So short wavelength, you may have destruction within like 50 or 100 meter from the coast, but for typical thrust faulting tsunami-genic earthquakes, you may have inundation, destruction within like several hundred meter, like 500 meter. Like just example, the Banda Aceh was, you can see many city was destroyed. The limit of inundation can be up to 5 kilometer inland, fast inundation by that. But that is giant earthquake. So yeah, but can be like, what about, let's see, 2006 Java tsunami. The inundation limit of inundation is up to 1 kilometer inland. Yeah, that's, you can tell the difference from the wavelength event. So basically, this is for this Anak Krakatau. It's like landslide source. Well, it's flank collapse. It's basically landslide, but the flank collapse was happened because of volcanic eruption.
Okay, thank you, Dr. Gusman. Another question from Priska. I would like to ask about how cold we differentiate flank collapse from pyroclastic flow.
What's that?
How could we differentiate flank collapse from pyroclastic flow?
Well, pyroclastic flow is very hot ash, so that's yeah, okay, it's tough actually. So because we don't have really, yeah, we don't have well, the the pyroclastic flow is hot material, and flying collapse is just like landslide going inside. So different material that generated the tsunami. How to differentiate that? I guess if it, well, pyroclastic flow, probably we don't necessarily have flying collapse. It's just like if this is just, I mean, after the eruption, they just spitting out the hot ash from the magma chamber, and then it's get out. So you don't really see the I mean the landslide. There was the volcano was relatively intact. So that's probably can say this, and the tsunami happened. So probably you can say, oh, that's from pyroclastic flow, and definitely not from flying collapse, because flying collapse you can see. I mean, just like the photograph from the Anak Krakatau, the volcano is just gone. So that the flanks totally collapsed. And probably there was also pyroclastic flow involved in the event. Well, I don't know. Well, yeah, but people think the easiest way, I mean, the easiest explanation, they would think, okay, once the flank of the volcano was gone, so that tsunami probably generated by the flank collapse. They don't really, what is it? We really talk about the pyroclastic for the Anak Krakatau event. It's hard. I don't know. I don't know if that answers your question.
It's okay. Thank you.
Unless we have the CCTV, we should probably put CCTV now in the surrounding the Anak Krakatau, so we can tell if it was a pyroclastic flow or flying collapse. So yeah, well, that's a good question. So maybe in the future we need to put CCTV, put tide gauges, radar, every kind of instrument, seismograph, seismometer there. Yeah. What do you think, Dr. Zul?
Yeah, I think we hope like that. We can observe with many instruments to know better about the mechanism of the Anak Krakatau, for example, and other activity in the volcano, maybe to know the better understanding of the mechanism.
Yeah.
But of course, it's not easy.
Yeah.
Yeah. Some of our instruments get the vandalism, something like that. Is I think another problem when we put the instrument in the remote area. It's not easy to maintain, of course. But I think this is a big job or a big homework to do this thing. Okay, thank you, Dr. Gusman. And then we have another question from Prima. Is there any way to measure the tsunami height if there was no watermark? For example, in case of no building or trees.
Yeah, you need the reference to measure the tsunami, but at least you will have like, I don't know, this is I think it's a very rare case where you don't have building or you don't have trees. You should have trees, especially in Indonesia. You should have trees, and if the tsunami was big enough, it will knock down trees. So that's a sign. And then usually we have sandy beach, and the sand would be basically the tsunami will bring the sand with the flow, and then it will deposit the sand inland. so that you will have a trace from the sand. So you have the limit of inundation. You probably will not, if let's say there's no trees, just flat, but at least you can give me sand, okay? Just a sandy beach. Like, I don't know. Well, sandy beach also, it's tricky. If it's like very fast sandy beach, like in south of Yogyakarta, you will have, the tsunami will bring the sand and then land it somewhere inland, but it's also already sand. So you will have sand and sand deposit that you will not be able to detect that. But if you have sandy beach and then like 100 or 200 meter from that, you have like grass or paddy field, I think you will be able to have like tsunami traces. So you will have the limit of inundation, and then you can measure the height of that limit of inundation. Then you will get the run-up height, not flow depth. Well, you don't give me trees between that, right? So flow depth, basically we get, if we have trees or buildings, so we get the flow depth.
Okay, thank you for the comment and answer. And then we have another question. I think it's the last one from Aldo. What is the most devastating historical event caused by the volcanic tsunami?
Definitely the one of the most devastating one is the Krakatau. Krakatau 1883. It killed like 36,000 people along the Sunda Strait, and then it's destroyed Merak, destroy Anyer, and destroy Kota Agung, destroy Kalianda, and Merak is flooded by 4-meter tsunami. So if you go to Merak, you can see, I mean, the place was kind of, you have an island in front of the port, and that's yeah, that kind of amplified the tsunami. That's why the tsunami there was up to 40 meter. So it's kind of, the wave was trapped between those small strait, I mean, between that small island. I mean, from Merak to that small island in front of the port. So the tsunami was 40 meters. So just, you can imagine, yeah, the town was completely destroyed. Yeah, I think it should be like 1883.
Okay, thank you, Dr. Gusman. I think it's all. Sorry, another question from Marco. Okay. Was the Anak Krakatau just a plain collapse tsunami, or there was also directional blast due to the collapse?
Yeah, so the main, we think the main the main cause was the flank collapse. That's what people believe. The explosion, well, we have blast, explosion several times, right? Not only one or two. But why we don't have tsunami record for those many blasts? So is that because the blast was too small, or just the blast didn't generate large enough tsunami to be detected? So we tend to think that the tsunami was generated by the flank collapse. Otherwise, we will have many tsunamis, right? But here we have only basically one large tsunami. And well, see, as shown in this previous studies, the duration is 7 hours. So the duration was 7 hours, but that is from the flank collapse scenarios.
Okay.
And oh yeah, there's, I think, well, in Merak, sorry, it's not 14 meter, but 40 meter. 40, even larger.
Okay, any else? The question or comment? Okay, I think it's enough, Dr. Gusman.
Okay.
Okay, please give applause to Dr. Gusman, because you can give virtual applause. Thank you, Dr. Gusman, for fruitful lecture today. I think we get a lot of insight from your presentation. Sorry, I saw Andre here. Any comment from Andre?
No, thank you. Thank you all. Thank you very much all. Thank you, Pak Adit. Yeah, see you again in Indonesia.
Okay.
Okay, thank you very much to all of you, especially to Dr. Aditya Gusman, who gave a lecture today. And tomorrow we have another topic, interesting topic. And the topic will be delivered by Dr. Irwan Melano and also Dr. Endra Gunawan. He will discuss about the deformation on the volcano based on GPS observation. Okay, I think we will close for our lecture today. Thank you very much for your attention, and keep health and stay safe for everyone. Good day. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.